Imagine standing on a world where instead of one sunrise, two suns slowly rise over the horizon together, painting the sky in colors we've never seen on Earth. The shadows stretch in strange directions, the heat pulses from two sources, and day never quite feels the same from moment to moment. It sounds like something straight out of Star Wars, a place like Tatooine. But this is not science fiction anymore. It's real. NASA has officially discovered a planet orbiting not one but two stars, and what makes it even more bizarre is the unexpected twist scientists were never prepared for. This discovery has sparked massive excitement in the astronomy world because it challenges so much of what we thought we knew about planetary systems. For years, we believed planets orbiting two suns were rare, unstable, or possibly even impossible to exist for long periods. The gravitational tug-of-war between two massive stars was thought to disrupt planetary orbits, eventually flinging them into space or crashing them into one of the suns. But this newly discovered planet is not only surviving, it's thriving in this unusual binary system. And that's not even the twist. What makes this system truly shocking is the planet's atmosphere, motion, and possible hints at conditions that no current models can fully explain. Let's rewind a little to understand how NASA found this mysterious world. The planet was detected by a combination of data from the transiting Exoplanet Survey Satellite, TESS, and the Kepler Space Telescope, two of NASA's most powerful planet-hunting tools. TESS first picked up some strange dips in light coming from a star system that had already raised eyebrows for its unusual behavior. These dips in light, known as transits, usually indicate a planet passing in front of a star. But this time the pattern didn't make immediate sense. It was erratic, unpredictable, and hard to model using single-star systems. That's when the scientists looked deeper and realized that there weren't one, but two stars in the system, each contributing to the gravitational chaos. And yet, despite that, the data showed a consistent planetary presence. This confirmed the existence of a circumbinary planet, a planet orbiting two stars instead of one. It's an extremely rare find. So far, fewer than 24 such planets have been officially confirmed, and each one teaches us something entirely new about how flexible and surprising the universe really is. This particular planet, temporarily labeled TOI 1338b, behaves in strange and fascinating ways. It orbits around both its stars in a near-perfect balance, completing a loop every few months, even as the two suns orbit each other in a complex dance. What amazed astronomers most was how stable the orbit seems to be. The planet doesn't wobble out of position, doesn't seem to be at risk of being pulled into one of the stars, and maintains a steady enough path for scientists to observe it over time. That alone is a big deal, because it proves that stable, life-hosting environments might exist even in systems that seem too chaotic on paper. But here's where the twist comes in. Upon analyzing the planet's light signature more deeply, scientists found something unexpected in the atmosphere. They detected strange chemical markers, things that didn't quite fit the usual planetary patterns. Early analysis hinted at a higher-than-expected level of metallic elements in the planet's upper atmosphere. And the weirdest part? These metals seem to come not from the planet itself, but possibly from debris circling around the binary stars, something like a shared cloud of gas and dust that gets slowly absorbed into the planet's skies over time. This could mean the planet is not just orbiting two stars, it's feeding off the shared material between them. Think of it like a planet growing by inhaling leftovers from the violent gravitational interactions of its two suns. This feeding effect could even be responsible for its unusual orbital stability. In other words, the very chaos we thought would destroy the planet might actually be what's keeping it alive. It's an idea that has turned planetary science on its head and opened up new models for how planets form and evolve in binary star systems. Scientists now believe that binary systems could be far more fertile than previously assumed. Instead of being destructive, the gravitational interaction between two stars might sometimes act like a cosmic cradle, gently rocking a planet into a stable orbit where it can gather mass, develop an atmosphere, and maybe even sustain life. That's still a far-off possibility, but discoveries like this are what keep the dream alive. And the discovery of TOI 1338b could be just the beginning. Another strange thing about this planet is its changing appearance depending on where it is in its orbit. As it swings around both stars, the amount and color of light hitting it changes constantly, possibly creating rapid shifts in temperature and even bizarre weather phenomena. Imagine one day being hotter than a desert and the next chilly with eerie twilight, even though it's still daytime. That's the kind of world we're talking about here. A place in flux, a living test of how different planetary environments can be under the influence of dual suns. But what about life? Could such a world ever support it? At first glance, it might seem too unstable, too unpredictable. But that's only if we limit our imagination to Earth-like conditions. The more we study planets like TOI 1338b, the more we realize life might adapt in ways we can't yet comprehend. If organisms evolved to handle fluctuating light, shifting winds, and varying temperatures, who's to say they couldn't thrive in a world with two suns? Now, imagine what it would mean if this strange planet, TOI 1338b, were not just a freak of nature but a signpost pointing towards something much bigger. What if planets orbiting two suns are not rare exceptions but a common outcome in the universe? That would dramatically increase the number of potentially habitable worlds. Binary systems make up more than half of all star systems in our galaxy. If these chaotic neighborhoods can still produce stable planets, the implications are mind-blowing. It could mean that the odds of life somewhere out there are much higher than we ever thought before. But to confirm such ideas, scientists need more than curiosity, they need data. NASA and international space agencies are now designing future missions that will target binary systems specifically, looking for more planets like TOI 1338b. These missions will not only search for planets but also analyze their atmospheres, measure their magnetic fields, and monitor their orbits over long periods. That kind of detailed observation takes years, but every piece of information adds another clue to the puzzle of planetary evolution. The goal is not just to find more planets, but to understand how they form, survive, and possibly become homes for life. TOI 1338b has already inspired a flood of new simulations. Researchers are using powerful computers to recreate the gravitational dynamics of binary systems. They're modeling how dust clouds collapse, how planets migrate, and how atmospheres change depending on light from two sources. One thing they've found is that binary systems may produce planets that are even more chemically diverse than those around single stars. This diversity could lead to more complex climates, unusual surface conditions, and environments that favor adaptability. And where adaptability thrives, life might just find a way. The presence of strange metallic elements in TOI 1338b's atmosphere is another tantalizing clue. On Earth, metals in the upper atmosphere usually come from meteorites burning up. But this planet's metallic signature doesn't fit that profile. Instead, it seems to be slowly collecting matter from the shared cloud of debris orbiting its two stars. This suggests the planet may be evolving in real time, constantly altering its chemical makeup based on the environment around it. That kind of planetary evolution is something we've never observed so clearly before. Imagine what kind of creatures could evolve on a planet with such a dynamic environment. If life ever did arise there, it would need to be highly flexible, able to survive temperature fluctuations, ultraviolet radiation from two suns, and constantly shifting light conditions. Some scientists believe that if life were to exist in such a place, it might not even be carbon-based like us. Instead, it might rely on silicon or other elements more abundant in this kind of system. That opens the door to entirely new categories of biology, alien life that functions differently from anything on Earth. Even if we don't find life, the physical processes at work on TOI 1338b are worth studying in their own right. For example, understanding how this planet maintains orbital stability could help us protect satellites and spacecraft in unstable gravitational zones. Learning how atmospheres respond to dual-star radiation could improve our climate models here on Earth. These may sound like distant benefits, but every mission in space has the potential to improve life on our home planet in unexpected ways. Public excitement around discoveries like TOI 1338b is also helping science gain momentum. When the public gets involved, funding increases, awareness grows, and new talent gets inspired. Schools are already using this story to teach students about physics, astronomy, and the vast potential of the cosmos. It becomes more than just a headline. It becomes a beacon calling out to the next generation of scientists, explorers, and thinkers. And let's not forget the cultural impact. Films, books, and video games are already imagining what life would be like on planets with two suns. So what's next for TOI 1338b? NASA is hoping to get more detailed data using the James Webb Space Telescope. Webb can study the planet's atmosphere in far greater detail, using infrared spectroscopy to detect molecules we couldn't see before. This could tell us whether the metallic elements are stable, changing, or reacting with sunlight in unexpected ways. Webb might even detect temperature variations that confirm how light from the two suns interacts with the planet's surface. All this will help create a complete profile of what daily life might be like on a world orbiting two stars. But beyond TOI 1338b, scientists believe there could be thousands more planets like it waiting to be found. Many of them might be smaller, closer to Earth in size, or located in the habitable zones of their systems where liquid water could exist. That's the ultimate goal of this exploration, finding a planet not just strange but familiar, a place that reminds us of home even if it has two suns. Every binary system is now a potential candidate, and the hunt is just beginning. And here's something poetic to think about. For thousands of years, humans looked up at the sky and believed Earth was the center of the universe. Then we learned we orbit one star among billions. Now, we know some planets orbit two stars at once. With every discovery, we're reminded that the universe is deeper, stranger, and more fascinating than we ever imagined. TESS 1338b is not just a planet. It's a symbol of how far we've come in our understanding of the cosmos, and how much more we still have to learn. As we continue exploring, we may one day send probes to study these circumbinary planets up close. Just as we sent rovers to Mars, we could one day land autonomous spacecraft on a planet with two suns. Those missions will take decades of planning, international cooperation, and technological breakthroughs. But make no mistake, they are coming. Because every time we find something as strange and beautiful as TESS 1338b, the question becomes not just what is it, but how do we get there? The twist in this discovery isn't just that a planet can survive orbiting two suns. The twist is that it might thrive, evolve, and maybe even inspire life. It turns out the universe isn't interested in our limitations. It writes its own rules, builds worlds where logic says none should exist, and challenges us to keep discovering. And as long as we keep looking, it will keep surprising us, again and again across billions of light years. So next time you look up at the sky, remember TESS 1338b. Remember that two suns can dance together, a planet can ride their gravity, and somewhere out there, an even stranger story might be unfolding. It's not just science. It's the next chapter in the story of us, and we're just getting started, where it's needed. But there are major hurdles too: targeting precision, energy loss during transmission, and safety concerns about high-energy beams hitting equipment or even humans. Interestingly, the moon itself might provide some power sources we've never considered before. For example, the regolith contains helium-3, a rare isotope that could potentially fuel future fusion reactors. If fusion energy becomes viable, the moon could not only power itself but export clean energy to Earth. However, fusion remains an elusive goal, still decades away from practical use. Let's not forget geothermal energy. While the moon doesn't have tectonic activity like Earth, recent data suggests that thermal gradients exist beneath the surface, especially near certain craters. If we can tap into underground heat, it could help maintain life support systems or reduce the energy burden on other systems. But again, this requires exploration, drilling tech, and infrastructure that's not yet in place. So what's the most realistic power mix for a future moon colony? Experts agree, it won't be just one source. The most successful lunar base will likely rely on a hybrid model. Solar panels for daytime efficiency, batteries and fuel cells for short-term storage, nuclear for long-duration baseload power, and possibly even wireless space-based energy transmission. This multi-layered approach is what gives a moon colony the best shot at survival. And as we build that infrastructure, we'll be testing systems that could eventually support Mars colonies or even deep space missions. The moon is not just a destination, it's a proving ground. The technologies we test there will determine whether humanity can ever live beyond Earth. But there's one more major challenge we haven't touched yet: moon dust. Yes, that seemingly harmless gray powder could be the greatest enemy of all power systems on the moon. In Part 2, we'll explore how lunar dust threatens solar panels, electronics, and even astronaut health, and what engineers are doing to fight back. We'll also look deeper into NASA's current energy strategy for Artemis bases and the long-term blueprint for lunar survival. So if you thought solar panels were enough to power humanity's next home, think again. The truth is more complicated, more exciting, and more urgent than ever before. We uncovered a major truth: solar power alone isn't enough to sustain a moon colony. But that's just the beginning of the challenge. Even if we manage to land nuclear reactors, set up fuel cells, or beam energy from orbit, there's still one silent, deadly enemy that could sabotage all our efforts: lunar dust. Known as regolith, this ultrafine material isn't just dust. It's razor-sharp, electrostatically charged, and gets everywhere. And it's one of the biggest threats to long-term survival on the moon. Let's break this down. On Earth, dust is rounded over time by weather, wind, and erosion. But the moon has no atmosphere. So the dust particles there are sharp, jagged, and cling to everything. They stick to spacesuits, scratch helmet visors, jam machinery, and, most importantly, cover solar panels, reducing their efficiency by up to 50% in just a few days. During the Apollo missions, astronauts reported it was like working in soot and fiberglass. Imagine trying to run delicate power systems while your solar panels are being buried in microscopic knives. This is a nightmare for energy infrastructure. Engineers are currently testing electrostatic dust repellent coatings, vibration cleaning systems, and even nanotechnology to keep panels and sensitive gear clean. But these systems need power themselves. So the more dust that builds up, the more energy is lost, and the more energy you need just to maintain your equipment. It's a vicious cycle. That's another reason why diversifying the power mix, beyond solar, is so critical for lunar survival. Now let's turn our attention to the here and now. What is NASA planning for its upcoming moon missions? Under the Artemis program, the goal is to land astronauts at the moon's south pole by the mid-2020s and eventually establish a sustainable base called Artemis Base Camp. This base will rely on a carefully layered energy plan: solar panels placed in near-continuous sunlight zones, battery backup systems for short durations, and experimental kilopower nuclear fission units for long-term energy generation. NASA is working closely with companies like Rolls-Royce, Lockheed Martin, and BWXT to develop mini-nuclear reactors that can fit inside a rocket and deliver up to 10 kilowatts of power for over a decade. That's enough to power several small habitats, a mining unit, and essential life support systems. These reactors are designed to operate autonomously, require minimal maintenance, and shield their radiation from human activity. They might be the most realistic option for lunar survival in the next 10 years. But even NASA isn't stopping there. There are experimental concepts being studied that go beyond what's ever been attempted before. One idea involves space-based solar power, placing giant mirrors or solar arrays in orbit around the moon, which could beam energy directly to surface receivers using microwave or laser transmission. This way, colonies on the dark side of the moon, or in permanently shadowed craters, could still receive constant energy regardless of the local light conditions. However, building such systems comes with enormous logistical and safety challenges. Targeting microwave beams requires pinpoint accuracy. You have to ensure the beam doesn't drift or cause harm. The conversion of energy from sunlight to microwave, then back to electricity on the ground, also leads to efficiency losses. And the cost of building such massive space-based platforms is still astronomical. But as launch prices fall and modular satellite technology improves, this may become one of the most powerful tools in the lunar energy arsenal. Meanwhile, scientists are also exploring in-situ energy production. That means using what's already on the moon, mining aluminum, hydrogen, or oxygen directly from lunar materials. These elements can be used in chemical fuel cells, or even to support small-scale combustion systems in controlled environments. This approach reduces the need to transport fuel from Earth, which is incredibly expensive. If ISRU, in-situ resource utilization, becomes viable, it could unlock true energy independence for future moon settlers. Another fascinating possibility is thermal energy storage. During the long lunar day, colonies can collect excess heat and store it in materials like molten salts or phase-change materials. Then, during the 2-week-long night, that heat is slowly released and converted back into electricity using thermoelectric generators. It's a method already tested in some extreme environments on Earth, and it could help maintain operations during the dark periods when solar is offline. But we need to be realistic. No single power solution will solve the lunar energy problem. It will take a layered strategy, a combination of solar, nuclear, chemical, space-based, and thermal energy solutions. That's the only way to ensure redundancy, flexibility, and continuous operation in a hostile, unpredictable environment. And as more international space agencies join the lunar race, like China's Chang'e program and India's Chandrayaan missions, the idea of energy cooperation and shared infrastructure could emerge as the next big step. And here's the bigger picture. The moon is just a test run. Everything we learn about building energy systems there will be applied to Mars in the future. Mars has its own solar problems. Frequent dust storms that can last weeks or months and block sunlight almost entirely. If we can't solve the power problem on the moon, we can't survive on Mars. The moon is our lab, our training ground, our sandbox for learning how to build civilization beyond Earth. So what would power a moon colony? Not just solar panels. Not just batteries. It's going to be a complex, multi-tiered network of power sources working together, backed by smart systems, adaptive AI, and redundant designs. From atomic heat to lunar hydrogen, from microwave beams to thermal bricks, we'll need every tool in the box to turn the moon into humanity's second home. And maybe that's the real lesson here. Colonizing space isn't just about exploration or adventure. It's about engineering survival in places that were never meant to sustain us. Power is life. And on the moon, we'll have to invent a new kind of life support system. One that runs not on hope or science fiction, but on pure, reliable, round-the-clock